There we go. Okay, so we have gone through the first week with the labs. Now, may I remind you that when you show up to the lab, it's just like you're showing up to work. So just have to make sure that you have your personal protective equipment, which is safety boots, hard hat, and safety glasses. Without any of those, I am not allowed to let you in the room. Okay. Also, please bring your tools. It's just like showing up for work. Imagine you are a boss or you're owner of a company that you have hired people and you pay money uh, for the workers to show up and do the work. And imagine what would happen if one of your workers shows up without the tools. Hi, I'm here. Are you happy? All right, just so bring your tools as well. And one last thing, please bring your padlock. Just a regular padlock that you can open and close, and you know the combination, or you have the key for it, because we have a set of lockers just around the corners, just around the corner from the lab room, so you can store your stuff like school bag, jacket, or whatnot. This room is very busy. We are not the only ones there, and the general idea of that is that anyone who shows up there, just show up with your tools and with yourself to be ready to do the work. Okay? We are not uh, well allowed. We are not to bring all your stuff because this room would just get too busy. And if you have watched the safety mm, lecture notes, if you read them, bringing extra things and laying them all over the place creates something like a tripping hazard. Okay, so that's the reason. All right. Okay, so last time we talked, we had the, we were talking about the multimeters part one, and just as a review, mm, now you can type on the chat lines or you can pipe in with the voice as I'm asking the questions. Just a review. When it comes to connecting a voltmeter, and voltmeter is a meter that measures the voltage. Voltage is the electrical pressure between 2 points. Um, so when it comes to connecting a voltmeter, are we connecting that device in series or parallel um, with the load that we are measuring? Anyone? We have series, we have parallel. Okay, so parallel. Okay. Screen share. There we go. You should be able to see me. Wonder if you see me there or not. Can you see my beautiful face on the screen share as well or not? Just so we have some personal contact as much as we can. No? Yes? All right, hold on. There we go. Just bear with me as there we go. And you should see my face there in the top right corner somewhere. And I'm going to bring up the chat so I can see things. And another thing. There we go. All right. Yeah, sometimes it takes a couple of seconds for this thing to kick in. So you should see the screen. You should see the screen share right now. Can anyone confirm? Yes. Okay. Good. All right. So when it comes to grab a pen, connecting a, let's say we have a couple of resistors, one resistor. These are ugly looking resistors, and they're connected in series. And let's say here is the power supply. And if we're having a voltmeter, yeah, with the terminals R1, R2, and if we want to measure R, let's say R2, are we going to connect this thing in series or parallel? We have different answers. Well, we're going to connect that thing just like that. And that is going to give us the voltage of across the resistor 2. This is plus, this is minus, whatever the voltage is, whatever the resistance is. And based on that, we're going to get the voltage of the voltage dissipated, or the voltage that occurs across R2. It's also called a voltage drop. Okay. Now, when it comes to the internal resistance of a voltmeter, do we need this thing to be high? Well, we're not setting it up. It basically, once we set the the multimeter, switch the dial to measure the voltage, it becomes a voltmeter, and its internal resistance is going to be what? High or low? We got high. Brian says high. Okay, anyone else? Okay, we do have the answers of high. Yes. And why is it that we need, well, if somebody is designing, if you're building from scratch a voltmeter, why do we need that resistance to be high? You can go on voice as well if you want. I'll give you a couple seconds to chew on this question here. Okay. Again, if we don't connect anything, if the voltmeter doesn't exist here, what is the resistance other than the resistances that are connected in the circuit? There is some other resistance that surrounds the whole circuit, and it is the resistance of the air. There you go. Thank you. And it just can't escape that. The air surrounds this resistor, and air has certain resistance. Right? And the resistance of the air is very high, to the point that when we are measuring our circuits that you're going to build in our school, you can pretty much assume that the resistance of the air is infinite, which means the circuit behaves as it behaves. So if we are going to tap in with something just to take a measurement, we want to take a measurement of what is happening in the circuit. We do not want to alter the circuit's behavior. So we need to have that resistance of whatever it is to be as high as possible to basically not affect the circuit's behavior. Now, when we talk about the amp meter, are we connecting the amp meter in series or in parallel? Connecting it in series. Good. So let's get an amp meter connected here. Here's the symbol of an amp meter with the letter A. amp meter measures current. What did we have before we connected the amp meter? We had the straight wire, and the resistance of the straight wire, yes, it has very little resistance. If you really want to go to the bottom of it, you're going to have some very low resistance because it's a wire, because it is made out of a physical object, which is metal. Could be copper, could be silver, could be gold. But the resistance of a piece of wire is pretty much zero for what we're going to study. Okay? So again, we want to take a measurement without affecting the circuit's behavior. So we need to have the resistance of whatever we tap in with in series. We need to have it as low as possible. So the internal resistance of a amp meter should be as close as possible to zero. Okay? So now, so that is the voltmeter and the amp meter. As a review, let's clear the board. And we're going to talk about also, as a review, about the measuring the resistance. So here is again, here is a resistor. We are going to again call it R1. And here we have an ohm meter. Here. And here, that's how you draw the omega symbol, okay? Now, you connect that to the resistor. And what is going to happen? When you switch the multimeter to an ohm meter setting, ohm, it comes from the last name of a person who was studying the resistance in the beginning of the studying of the resistance stage. Okay? So the unit of resistance is named after him. So what happens when you are measuring resistance? So you switch the dial of a multimeter to an ohm meter, and it becomes an ohm meter. What happens is that the ohm meter is going to introduce its own power in order to create a current flow through the measured device. That's how the current flows. And the only way the current flows in this case is going to be through this resistor. Right? It creates a little tiny bit of a voltage, and different multimeters have different voltages on their leads. There's no set standard. Usually it's around 2 volts, but you can measure that next time you're in class. Just take 2 multimeters, set one to ohm meter and set one to the voltmeter. So one is going to be the ohm meter, the other is going to be the voltmeter, and just connect the leads to each other and see with the voltmeter, see what voltage the ohm meter is going to introduce across its leads. All right. So when the ohm meter introduces a little bit of a voltage, it creates a current, and if there's a current and the current meets some sort of resistance, set resistance to whatever it is going to have well, current flowing through it. And based on the amount of current and the voltage that's introduced, that's the formula, the Ohm's law. You're going to study that. All right, there. All right, voltage equals current times resistance. All right, so if you want to measure the resistance, the multimeter is so smart that it's going to calculate the resistance because it knows what voltage is putting out, and based on the voltage is going to measure the current, and it's going to calculate the resistance. So how do we get the resistance out of that? Well, we have to do the same thing to both sides of the equation in order to keep the equal sign. How do we isolate R out of this part here, right here? Well, we divide this side by I. So means if you want to keep the equal sign, we have to divide the other side by I. So if you divide that by I, you're going to have just R here, and divide the other side by I. So you're going to have voltage over current. And that's how the ohm meter calculates the resistance. And again, clear the board. I'm going to show you something that you have access to. Right? Now, I'm going to find out whether you are eligible to download the student version. I think you are eligible for that. You got to talk to the IT department. This is the software I'm talking about is called Multisim. Did anyone use Multisim at all? If you haven't, it's a good idea for you to use that. It's a very helpful software. It is not the reality because nothing can substitute the reality. But if you use the multisim, it's going to help you with some idea of what you might expect. Right? So I do happen to have a copy here. Here is what multisim looks like. And when we showed you the homework lab, it's right by the bus's entrance. There's a big room. Actually, our school has many homework labs. Um, uh, Multisim should be on those computers. So this is a building T, right where the buses are. Um, as soon as you enter, you can, if you keep walking straight, you're going to hit that room, big room with lots of computers. That's a homework lab. You can just go in there and you're welcome to use it. And it should have multisim installed. If it doesn't, just call the IT and tell them that you want that you need multisim installed at the machine that you're at, and quite often it's going to take a couple of minutes, but they should have that thing installed. There's a question here from Katie. Did I pronounce your name right? Did I say the contact ID to download it? Yes, contact ID, and I'm 99.9% sure that as our students, you can have a student version on your computer, but please confirm that with the IT, and I'm going to check it out as well. Right. So here's what multisim looks like. Let's take a look at some. I'm going to show you some of the basics of that, and we're going to play with some voltmeters and current meters or amp meters. All right, so this is the starting screen, and I'm going to go and place. I'm going to place a component. Okay. Now, when I said place a component, do you see the sub screen moving? And has a little symbol of a diode, because sometimes when Zoom shares the screen, it's funny. So when I do the place component, there should be another window that is within the window right now that I'm actually moving the whole window from left to right. Can you see it? Okay, I hope you see it. Brian says, yes, you can see it. Okay, good. So when you place a component, again, I'm going to go place component, and I'm going to make sure that it's a master database, all groups, all families. That's the entry point of entry here. So what I'm going to do is, well, in that component here, you can type resistor. And it's going to give you a resistor. Or you can go to the all groups and select the basic components. So this here, the basic, and it gives you a resistor, and you can choose any value of the resistors here, of the resistor, or you can just click OK, and it's going to basic resistor. There we go. Okay, and it's going to give you some sort of a resistor. I'm zooming in. So I'm going to place that, and right off the bat, it's going to show you that it's R1 and it's 1 kilo ohms, or 1 kilo ohm. Right, and if you don't close the window, it's going to give you the option of choosing another component that is the same. All right, and if you keep clicking OK, it is going to keep giving you the resistors. All right, so I'm going to close the window, and now I can rearrange this these components. Now, if you double click on it, or if you right click on it and put properties, or if you can just double click on the whole thing, and if you can see, this shows the value. So you can have a value of 1 kilo ohms, or 1 kilo ohm, which is basically 1000 ohms. You can do this like that. 1000 ohms, it's the same thing, and see that the value has changed. All right, now let's say this one here, we're going to do 2 kilo ohms, 2 kilo, which is 2000. And here, instead of 1000, we're going to say 1 kilo. Okay, and let's make this one let's make this one 4 kilo. I'm just going wild here with the values. All right, now let's connect these three in series here, and making connections is simple. Now let's place another component. Place component, and let's go with sources. Where are the sources? There you go, sources right here. All right, and we're going to go with power sources, and we are going to choose DC power, and click OK, and we're just going to place it. And we don't like the way it is placed, so I'm going to just choose it, click once on it, and if you go Control R, and click, it's going to rotate that. See, I can keep rotating by pressing Control R. I like it this way. All right, and again, we're going to place another component, and let's go crazy here. You know what, since we are here on the source, in the sources group, we need a ground here, because multisim wants grounds to be present. It just won't let you operate the circuit if you don't have ground. It's just the way that it. And the other thing is, I'm just going to go to all groups, and over here I'm just going to type something SPST, and it's a single pole single throw switch. Single pole single throw. What happens if you said single pole double throw? Oh, it gives you a single pole and double throw. You can switch the pole here or here, but we want just a single pole single throw switch. Okay, and we're going to place that thing right in this here. Now it says key equals space. That means if you press space, you're going to operate the switch. See? Okay, I'm pressing space. You can choose another. If you just double click on, if you double click on it, you see here key for toggle, and you can choose anything. Let's say I'm going to choose A, all right, and click OK, and it says key A. So now I'm pressing key A to operate that. Space will not give me anything now anymore. Right? So that, but you know what? I'm going to double click on it again, and what I will do is I'm going to display values. and you can choose what you want to be displayed. And just to get rid of the graphic pollution on this screen here, I'm going to use the component specific visibility settings, and I'm going to uncheck everything. Okay, and now we have a clean switch without things being displayed. You can call up the display whatever you want. Now, so we have V1 12-volt DC. We can also change. You see, if you go double click on it, or if you right click and call properties, comes the same thing, value, and you can change the value. Let's say we have 10 volts here. Right? See, it changed. Okay. So I'm going to kind of place the ground somewhere else right now, and I'm going to, let's say, I'm going to rotate this so I have the positive on the left side here. So Control R once, twice. Okay, good. That's the positive side. That's the negative side. And let's do the connections. Connect this to here, red thing to the blue thing, uh, here and here, and or we already connected these guys. So connect something like that, and we have a closed circuit, and we are going to connect the ground somewhere here. Yeah. Circuit's not working yet. Now, when we press the play button, that's when the simulation begins. So we press the play button, and now we have the virtual reality in the screen. We can click on the switch and close it. Oh, we have a current flow here. Can you see the current flow? Of course we can't. That's why we use the measuring equipment. So let's tap in with a voltmeter. All right. In order to change anything, that's the only thing I don't like about the multi-sim is if you move your mouse somewhere, it's going to change the way it is displayed on the screen. It's going to move your screen left or right. Multi-sim, please take care of that thing. It's annoying. Right, so I'm going to press the stop button to stop the simulation. And now I can add new things. Let's add a multimeter. All right, and the multimeter is in the tool set right over here. So, and the multimeter is the first one on the top. Why not? Click on that. And once you click and release, you are going to have a multimeter somewhere, and it is going to follow the mouse until you click again to place it. Right, well, let's place it over resistor R1. Boom. How do we connect the multimeter? The voltmeter, we connect it in series. Sorry, in parallel. The voltmeter, we're connecting in parallel. So here and here. I'm just going to move that a little bit. All right, here, delete and make it again. All right, let's connect another multimeter. Grab it here, connect it here, connect it here, and let's grab another multimeter. Oh, wow, we're going crazy here. Let's make it nice and pretty. All right, here, and there you go. This one has a crooked leg. All right, now, if you double click on these, you're going to call up the display. So I'm going to double click on the multimeter number 1. Click, click. And look, this screen shows up. You can place it anywhere. So we're just going to put it here. Open the switch. And double click on the other one. The display shows up. We're going to bring it here. So this one corresponds to that. This one corresponds to that. And let's get the third one. Okay, so now we have 3 multimeters. And we're going to make sure that these are set up as voltmeters. So you can choose different function of this here. So we're going to choose this thing to be a voltmeter. And instead of AC, we're going to make sure it shows up as DC. All right. Voltmeter, DC, voltmeter, DC, we're good. Well, let's turn the circuit on and see what happens. Okay, press play. Oh, look, some of the voltages come up. And of course, this one is connected wrong. I'm going to stop the simulation. Of course, it's showing 0 volts because we're measuring across the wire. So let's eliminate that. Just going to move a little bit here. This one goes here. And this one goes here. Okay. Turn it on again. You see what we have here? We have 99.993 something volts. And we have 199 something volts. 399 something volts. What is that something? Well, that something here is, remember when we said kilo, that means 1,000. There you go, that's micro. And micro is a Greek letter mu. It's just like U, but with a crooked leg here. But when we have the English keyboard, you're going to see just like a U here. But that's not U, it's supposed to be that micro thing, which is the letter mu in Greek. All right, so that it's micro, it is micro. It gives you the value, whatever the value is, x times 10 to the negative 6. The opposite of micro would be mega, and mega is whatever the value is times 10 to the 6th. So this is a million. And this is the opposite, is 1/millionth. So we're having a pretty low voltage here, 99.993 millionths of a volt. So it's such a tiny microscopic voltage. Well, the multisim is simulating the ambient noise that is on the resistor. Okay. Let's close the switch. Remember, we have to have that play button so that it is we have the circuit on. The simulation is on. Let's turn on the switch. Oh, we are getting some voltages happening here. All right. Well, this voltage across this resistor is 1.429 volts. The voltage across this resistor is 2.857 volts. And the voltage across this resistor is 5.714 volts. And if you have a calculator, if you add these three, this one here, and that one here, you're going to get 10 volts. Now, let's see if we can connect an amp meter. So what I'm going to do, switch the ground here. Oh, see what happens is that I'm going to erase that, extend it a little bit. There we go. Put the ground aside for now. Switch those around a little bit. And we're going to interrupt this line here. And let's get a multimeter and stick it right here. We can rotate that a little bit. So I'm going to go Control R. And that's better. So what we're going to get is this side of the amp meter. We're going to connect here. And this side of an amp meter, we're going to connect We are going to connect here. And now we have a complete circuit again. Click on that, double click, call up the display for the amp meter. Now, oh, it's not an amp meter. We have to make sure that's an amp meter. Okay, so now it's an amp meter. Turn the circuit on. And what do we have? As the main current in the circuit, we have 1.429 milliamps, which is 1.429 times 10 to the negative 3. The opposite of milli is kilo, is whatever is the value times 10 to the third. So this is 1.429, a thousandth of a amp. Right? All right, so it's a pretty low current, but this is the current in milliamps what we're going to be dealing with when you're going to do your labs in other subjects. All right. What happens if we switch that to a voltmeter and we have it in series? Stop the circuit, switch it to voltmeter, turn it on again, and flip the switch on. Oh, we have 10 volts across the voltmeter, and we have pretty much no current happening. As no voltage is happening here. Same, we go back to microvolts, which is basically the ambient noise that is happening across the resistors. Because remember, the internal resistance of a voltmeter is high as infinity. So you're going to read the whole voltage on that, and we're going to have no current flow. All right. Now, what happens if stop the circuit? We're going to go back to that amp meter here. So now we have an amp meter again, so with a resistance of like 0. And let's switch one of these to a amp meter. Let's get this one to be an amp meter. And it's connected in parallel with the load. Oh, we're going crazy here. Switch it on, turn it on. All right, well, what happens is we have different voltages here now. We have 3.333 volts, and we have 6.667 volts. Well, the main power supply is 10 volts. If you add this value and this value, which is this voltage and that voltage, you're going to get 10 volts. And this one shows 3.333 milliamps, which is kind of ridiculous. So you can ignore that value. It should pretty much, well, you know what? No, it's not ridiculous. Don't ignore that value. Look at this. This here took the whole thing. It's just like eliminated this resistor because now we have a wire across the resistor. And the main current now is 3.333. So it's just like we disconnect the resistor here. Oh, come on. We disconnect the resistor, put it somewhere else, and we just have an amp meter here and an amp meter here. Turn the circuit on. Again, you have 3.333 milliamps, right? It's just like having a wire. Now, or it would be just like having the resistor here, disconnect this amp meter, we just put it aside. I think that belongs to here. Okay, and we have a wire bypassing this resistor. Again, we have 3.333 milliamps as the main current, and the voltage across here is 3.3. The voltage across here is 6.7. Add these two, you're going to get 10 volts. Okay, let's do something else here. I'm going to close that, close these, close all of it. Simulation is stopped. Erase all the connections. Here. All right. Now let's arrange these resistors in a different way here. Let's connect this multimeter to this resistor. What are we going to get a reading? If I just double click on that and we're going to make it an ohm meter. Right. Start the simulation. It reads 1 kilo ohm because it is connected to 1 kilo ohm resistor. Let's go nuts here. Let's connect an amp meter here. And click on that and make it an amp meter. Turn the circuit on. All right. Now, this one shows 1 kilo ohm still, and this one shows minus 10 nanoamps. Why is it minus 10 nanoamps? Why is it minus? Because here is the positive side, here's the negative side, and the negative side is connected to the positive side. So that thing is going to show you the negative value. So let's stop that and correct this thing. Disconnect, disconnect. Mind you, if it was an analog meter, it will try to bend the needle the other way and you might actually damage the multimeter. The digital multimeter is going to show you the negative sign. All right, so we're going to click on that and right click on it, and we're going to flip it horizontally. Okay, now we have minus and we have plus. Okay, good. So here, 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 turn it on, and it's going to show 10 nanoamps. And nanoamps is a very small current. Well, it is 10 to minus 9. Okay, 10 to the negative 9. So whatever the value is, so it's 10s, it's 10, this value here, times 10 to the negative 9. So it's a very small current. Milli, micro, nano, pico. Pico is to the negative 12. All right, so now we know that this applies power. What is the voltage that it's putting out? Well, you can calculate using that Ohm's law. You have the resistance value, you have the current that's going through it, you can calculate the voltage that this one actually puts out. Or you can just connect one meter to another. Now, remember, it showed that here, 1 kilo ohm is the resistance value of this resistor. It shows that here. Good. Let's go crazy. Let's connect another resistor. I'm going to get that here, get that here. You know what? Erase, erase, erase. Here. Let's connect another resistor in parallel to that. Okay. This resistor has 2,000 ohms. This resistor has, sorry, this one has 1,000 ohms. This resistor has 2,000 ohms. What is going to be the total resistance of these two resistors connected in parallel? Well, let's simulate the circuit. Oh, it shows 666.67 ohms. Interesting thing. I wonder if somebody can notice one thing. Let's connect another resistor here. This one that is 4 kilo. Here and here. Simulate again. Oh, now the resistance is even less. The total resistance is even less. Okay. Well, let's copy this whole thing. And we're going to, just so I don't have to place components again. All right, let's connect them in series. And that is also an ohm meter. Is it still? Oh, there we go. So that's an ohm meter. Let's connect that in series. Yeah. Same 3 resistors connected in series. Same 3 resistors connected in parallel. All right. What is that going to show? Oh, this one shows 7 kilo ohms, and this one shows just shows 571 ohms. Ooh, what's going on here? Well, you probably know that. Some of us know that when we connect the resistors in series, we just add the values. So 1 kilo plus 2 kilo is going to give us 3 kilo, and the 3 kilo plus 4 kilo gives us 7 kilo. But what's happening here? This is 571. And if you notice, the total resistance of the resistors connected in parallel is going to be less than the smallest resistor in the circuit. See that? Let's go crazy here again. We're going crazy a lot here. Place component, basic, resistor, resistor. Place that, close the window, double click to choose. Let's make that 500 ohms. Yeah. And according to what we said, the total resistance is going to be less than the smallest resistor in the circuit. Oh, let's confirm that. Smallest resistor in the circuit is 500 ohms. This is 1000, this is 2000, this is 4000, this is just 500. Well, let's see if it's going to be less than 500. Oh, it's 266 ohm. It's much less than 500. Why is it? Well, excuse me. Why is it like that? Well, if you think about it, you are adding the resistance in series. So you just, here's resistance, here's more resistance, here's more resistance. All right. So the total resistance of resistors in series is going to be more than the whole thing. Now, if we just have R1, whatever else is there is, again, the resistance of the air, which is infinite for our purpose. What we're adding one more pathway, if we add another resistor to that one, we are adding another resistor that is less than the resistance of the surrounding air, because anything is going to be less than surrounding air. So you're providing another pathway for the current to flow. You add one more, so you're making this whole circuit, you're making for the current easier to flow by adding the resistance in parallel, because you're providing one more pathway for the current to flow other than the air, which is hard for the current to flow in the air. Right? Just think about what I just said. Now, we're almost done here. We got 10 minutes. One thing I'm going to show you, because I'm going to point you to another part 2 of the multimeter videos, and this is again the explanation of the terms that we're going to use. That quickly stop the simulate. Oh, it stopped. Erase the whole thing and erase the connections, erase the connections, erase the connections. Here, Erase that. Let's make things nice and clean. Here's our switch. Let's get something like component and basic. There, diodes. 1N4007 is pretty much a standard rectifier diode. You're going to study those. And I'm just going to display nothing on that. I just want to have a diode symbol. That's all I want. 1 kilo, that should be fine. Let's raise that to value here. Let's make it 12 volts for kicks. All right. Now, there you go. Place the switch here. Make a connection. Make a connection. Here, 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 here. Let's make this one 600 ohms. Okay, so it's 600 ohms here. And make a connection. Get the multimeter here. Get the multimeter here. Connect that across the diode. Connect that across the diode. There we go. Quickly call up the display, click on, call up the display, click here. We got volts, we got volts. Simulate the circuit. Kaboom, turn the switch on. And we have an error. Let's raise the value of the resistor. See, maybe that helps. 1 kilo. Oh, they need a ground. That's what they want a ground. Here, here, there we go. What do we have? We don't have enough. Let's go 470 ohms on the resistor here. Turn it on. All right. So what do we have here? We have 12 volts, main power supply. We have 11.296 volts across this resistor, and we have 704 millivolts, which is pretty much 0.7 of a volt, because this is, if you multiply it by 1,000, you're going to get the unit and you're going to drop the milli. Right? So we have 0.7 volts here, and we have the rest of it is going to be on this resistor. All right, let's do something else. Let's raise the voltage on that. Let's go 15 volts on the power supply. Excuse me. All right, simulate the circuit. Oh, look, we still have 0.7 volts on the diode, and the rest of it is going to be on the resistor. What happens is the voltage, the diode, you're going to study diodes, but the diode is a semiconductor. It only conducts one way. If we reverse the power supply, it's not going to conduct the current. It has to be the positive. Here's the anode, which is the positive, and here's the cathode, which is the negative. And we have a current limiting resistor. If we don't have the resistor, we're just going to burn the diode so fast that you won't even blink. All right, so what happens is that a diode has to have certain, it's called forward bias voltage, which means we have to cause enough voltage across the diode, and it's a silicon diode. So the silicon diode, the forward bias voltage is 0.7 volts, and that voltage is going to stay across the diode no matter what. if you raise the voltage high enough, you're going to burn it, but it is the voltage across the diode will not exceed 0.7 volts. Once it reaches that, it stays there. The rest of the voltage is going to dissipate, or is going to occur on the rest of the circuit. Now, that's a silicon diode. Then there's also a germanium diode. It has 0.3 of a forward bias voltage, and it stays. You're going to study that. Right. I'm not going to give you many more details, but I'll tell you, you're going to study that in your, I think it's your DC circuits, I'm not sure. I'm pretty sure you're going to study that. Now, when it comes to LEDs, light emitting diodes, the LEDs have different composition, different chemical composition to create a different type of light as current passes through it. And different chemical compositions will cause a different forward bias voltage on the LEDs. Quickly, can we get this? No. I'm going to show you the next time. If you get the LED here, this voltage is going to be different. So that's what I'm talking about when I am connecting the multimeter and testing diodes and showing you the functionality of the multimeter as a diode tester. The diode tester on the multimeter, the idea is that it should show you the forward bias voltage on the diode, but sometimes the voltage that is created on the multimeter is not enough to truly display the forward bias voltage on all the LEDs. So that's what I'm demonstrating on this video. Where is this video? The video is right here. If you go to main class portal, announcements, 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 here's our YouTube playlist. And already I put that thing on. It's a safety 1051 21F week 2 lecture 2B multimeters part 2. So here's your, well, it's a bit longer, but please watch it. This is going to help you with other subjects as well. By request from previous years, we are doing this as the first couple of lessons. So now I want you to be comfortable. You're not going to be very comfortable right off the bat. Just get that thing, going. You're going to have circuits, DC circuits, and you're going to have labs in them. So make sure you bring your multimeter, make sure it's unpacked, make sure, the other thing is when you're having your lab, please do not have your multimeter in your bag. Your multimeter should be on your desk as you're doing the lab, because sometimes you're going to have to troubleshoot the circuit. Sometimes you're going to have to measure this or measure that. Have it already in the ready position on your desk. All right. Well, 1 minute to go. Do you have another class after this to go to? Yes, no, maybe? If you do, I apologize. I should have let you out a little bit quicker, but with the beauty of online lessons is that this thing is recorded, and as I posted on YouTube, and it's going to be right before the last one here as a preamble to the part 2. I need you to watch that. It is not going to be always like this, that I'm going to ask you to watch the videos, but the videos that I did last year on the multimeters, I had so many props and I had such a big setup there and I'm happy with those. So I just want you to watch that. I'm not sure if I can repeat it exactly the same way. I'm pretty sure I could, but once I get my setup upgraded here. But I want you to get the full benefit of that. So that's why I'm pointing that. It's not going to be always. I'm going to give you that extra time to spend on. It's the beginning of the course. The beginnings are always hard. It's going to smooth out. Anyways, 9 o'clock, right on the hour. I will see you when I see you in the labs. We already have talked about what we need in the labs. And thank you for your attention, and I'll see you next time.